Hello, student. Welcome to this topic of digital to analog conversion. This is a chapter from the paper Electronic Circuits and Devices. So, uh, the basic problem in converting a digital signal into an equivalent analog signal is to change the n digital voltage levels into one equivalent analog voltage. That means this conversion process is sometimes very necessary for some devices where a digital signal is to be converted into analog one. For example, sound box, a speaker, the audio signal is to be given to a speaker, which is popularly called as a sound box or speaker. So that speaker, which reproduces the sound, requires an analog signal. It doesn't works on a digital signal. Just an example. Suppose that a audio signal is coming out of a digital circuit that cannot be directly fed to a speaker to reproduce the sound. So that has to be converted into first the analog signal, then it has to be given to the speaker, then only the speaker works. So this is just an example. So there are many devices which needs only the analog signal. So that is why initially, if the signal is in a digital form, that will have to convert into the analog form. So this basic conversion of digital to analog conversion, we have generally n number of digital signals, and all signals have to be converted into one equivalent analog signal. This is what we are doing in the digital to analog conversion. So the digital voltage levels, the n number of digital voltage levels are fed to one circuit. So that converts all the digital signals into one equivalent analog voltage. So this process is called as the digital to analog conversion. This is generally achieved by designing a resistive network that will change each digital level into an equivalent binary weighted voltage or current. So this process is generally done by a resistive network. So that will change each digital level into an equivalent binary weighted voltage or binary weighted current. So this binary weighted voltage is sometimes generally called as the binary equivalent weight. We'll see what is this binary equivalent weight. To understand this, a binary equivalent weight is a voltage level produced by a resistor network for a given digital input signal. So for example, consider a 3-bit system. This is a 3-bit system. Why it is 3-bit system? Because here 3 digital inputs are there. 3 primary digital inputs are there. So this is the bit 1, this is the bit 2, this is the bit 3. So these bits are nothing but the inputs, digital inputs. So here you can give the 3 digital inputs, so it is called as a 3-bit system. So here, so these are the different digital inputs or digital voltage levels. And here 0, 0, 0, we have to read these digital inputs horizontally like this. 0, 0, 0, this is one digital input. 0, 0, 1, this is another digital input. Like that you have to read. And here a 0, 0, 0 digital input is set equal to 0. First one is set equal to 0. And a 1, 1, 1 digital input is set equal to 7 volt, just for example. So here 1, 1, 1 digital input is there. I will set this as a 7 volt. Then what I will do, I will divide this 7 volts into 7 levels, and like this. This is 1, 2, 3, like that. 7 levels are created here between 0 and 1. 1 means the 7 volt. Then this, as I have given here, a digital 0, 0, 0 input produces the 0 volt. First one, no voltage is produced here. That means all the inputs are grounded. We can say that all the inputs are grounded, so no output will be there. And a 0, 0, 1 signal produces 7 into 1 by 7 is equal to 1 volt. Where is the 0, 0, 1 signal? This is the 0, 0, 1 signal. So here 1 is below this 2 raised to 0 position. 1 is below this 2 raised to 0 position. And this 0, 0, 1 signal produces 7 into 1 by 7. This 1 by 7 is called as the binary equivalent weight of this signal. So this 1 by 7 is the binary equivalent weight of this 0, 0, 1 signal. That means it produces a voltage of 1 by 7. So that is why we are multiplying this 1 by 7 into 7 to get the 1 volt. So here 1 is in the 2 raised to 0 position. 1 is in the 2 raised to 0 position. Similarly, a 0, 1, 0 signal produces 7 into 2 by 7 is equal to 2 volt. So that means 2 by 7 is the binary equivalent weight of this signal, or it is the binary equivalent weight of this 2 raised to 1 position, or this bit 2 raised to 1 bit. And a 1, 0, 0 signal produces 7 into 4 by 7 is equal to 4 volt, because this one is in a 2 raised to 2 position. So this 4 by 7 is the binary equivalent weight of that 2 raised to 2 bit. So in this way, the digital signals are converted into binary equivalent to binary weighted voltages like this. The 1 volt is produced here, 2 volt is produced here, 4 volt is produced here. So the circuit is designed in such a way that the value of each bit is twice that of a preceding bit. So the meaning of this sentence is that you can see here, this 100 signal produced a voltage of 4 volt, whereas the 010 produced a voltage of 2 volt. So this so this 4 volt is the twice of this 2 volt, which is preceding signal. So this 2 volt is the 2 times the voltage produced by this 001 signal. So in this way, the circuit is designed so that the value of each bit is twice that of the preceding. So it is the twice of this, and this is the twice of this, so on in this way. Then how the Then how the intermediate voltage levels are produced. To produce the intermediate voltage levels, for example, 3 volt, you have to combine two primary digital signals. Like you will have to use this 001 and 010 digital signals combine to, and these are combined to produce an voltage of 3 volt. So the intermediate voltage levels are produced by combining the two digital signals. The value of least significant bit LSB, which is 2 raised to 0, is calculated using 1 divided by 2 raised to n minus 1. This formula where n is the number of bits. So in this 2 raised to 0 position here, this 2 raised to 0 bit is called as the LSB, least significant bit, whereas this is 2 raised to 2 for the 3-bit system. This 2 raised to 2 is called as the MSB, the most significant bit. So this is referred as the first MSB. This is 2 raised to 1 is referred as the first MSB, and this is simply called as the MSB, that is the most significant bit. That means that this bit will be having the highest value, highest binary equivalent value. So that is the meaning of MSB and LSB. So this is the LSB and this is the MSB for this 3-bit system. So this MSB will change according to the bit system. Suppose if you are considering a 4-bit system, then 2 raised to 3 here, 2 raised to 3 becomes the MSB. In that way it continues. So how to calculate the value of least significant bit, which is 2 raised to 0, and for that we'll have to use this formula 1 divided by 2 raised to n minus 1, where n is the number of bit. Thus LSB for 3-bit system is 1 by 7. So for 3-bit system, this n is equal to 3. 2 raised to 3 is 8. 8 minus 1 is 7. So it is 1 by 7. This is also shown here. Means this for this 001 signal, which has a binary equivalent weight of 1 by 7. This 1 by 7 is the LSB, because this 1 is in the 2 raised to 0 position, or it is in the LSB position. So it is having a binary equivalent weight of 1 by 7. Similarly, and for that of a 4-bit system, for the 4-bit system, this n, small n is 4. It is 2 raised to 4. 2 raised to 4 is 16, and 16 minus 1 is 15. So the value of LSB for 4-bit system is 1 by 15. And next, the second, third, and fourth dash 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 bits means MSB. MSB values are obtained by multiplying 2, 4, 8 dash 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 to LSB. That means to get the first MSB, we have to multiply 2 to the corresponding LSB. To get the next MSB, means second MSB, you will have to multiply 4 to that of LSB. So in this way, it continues. So this is about the basics of binary equivalent weight. And now we will see a first digital to analog converter circuit that is called as the resistive divider circuit. So a circuit or network which converts digital signal into an analog signal is called a resistive divider network. So this resistive divider network is one of the type actually. The block diagram of a 3-bit resistive divider is as shown below in this figure. The corresponding voltage levels are shown in this figure. So once again, I am showing here a 3-bit system. So here resistive divider network will be there. To this network, 3 inputs are given: 2 raised to 0, 2 raised to 1, 2 raised to 2. So these are the bits, input bits. And this resistive divider network gives one signal, that is the analog output. So, again, just like earlier, if you are setting this 111 digital signal into 7 volt and 000 digital signal to a 0 volt, you can divide this 7 volts into 7 levels, and corresponding you will get the different analog signal for the different digital inputs. So these are the different digital inputs and corresponding analog voltages produced by this resistive divider network. So the resistive divider must do two things in order to change the digital input into an equivalent analog output. So, how it does? It does in this way: the 2 raised to 0 bit means the LSB bit must be changed to +1 volt. So when there is 1 under this 2 raised to 0 position, it must be changed to +1 volt, and 2 raised to 1 bit must be changed to 2 volt. That means when 1 is there, or when the digital input is given to this 2 raised to 1 bit, it should produce this 2 volt. And similarly, when the digital input is given to this 2 raised to 2 bit, it should produce the 4 volt like that. So it will do like that. And these 3 voltages representing the digital signals, digital bits must be summed together to form the analog output voltage. That means all these digital inputs means output of these digital inputs are summed or added to form a one analog output voltage. So the resistive divider network is like this. It is as shown in the figure. This is one of the resistive divider network, simple resistive divider network, or it is the construction of a simple resistive divider network. And resistors R0, R1, and R2 form the divider network. So here R0 is here, R1, R2. These are the resistors, and the load RL is very, very greater than R0, and hence does not load the divider network. So RL means it is a load resistance. It is a load resistance, and its value is very, very much greater than this resistor of divider network, and hence there will be no effect of this load on this resistor network. And you can see here the resistors are chosen in such a way that if it is R0, then R1 is R0 by 2, means half of this half of this half of this value. Then R2 is equal to R0 by 4. That means it is R2 is 1/4 of R0. In this way, these resistors are chosen, because the voltage drop across here and here should be changed. So that is why the resistors are used in that way. The analog output voltage of the resistor divider is easily found by use of Milliman's theorem, who states that the voltage appearing at any node in a resistor network is equal to the summation of the currents entering the node divided by the summation of the conductances connected to the node. So here nodes are there. This is actually, you can see here, If you consider this point, it is one node, or this is another node. So you can see here the currents which are coming here and here in, they are all coming to this common point and where they are added. So that is why summing action is there. And so that is why to get the output here, only you are getting the analog output from this point and the ground. So that can be obtained by making use of this Millman's theorem. So this Millman's theorem states that voltage appearing at any node in a resistive network is equal to the summation of the currents. You see here, these are the currents according to Ohm's law. V is equal to IR, or I is equal to V by R. So this shows the current. This is also the current. This is also current. So this is the current 1, current 2, current 3. So according to Milliman's theorem, we have to add the currents, sum the currents which are coming at a different nodes divided by sum of the conductors. So this is the input resistor present at input 1, bit 1. This is also the input resistor. So when you are taking reciprocal of these resistors, you are getting the conductances. So these are the conductances which are also added. So divided by the summation of the conductance connected. So these are the conductances and these are the currents. So their sum gives the output voltage of this resistive divider network. Then so this is very simple resistor divider network. It converts the digital signal into the analog signal. So because of its simplicity, it has the drawbacks. So what are the drawbacks of this the resistor divider is that each resistor in the network has a different value. So we have seen here, this is R0, R1, R0 by 2, R2, R0 by 4, and for another bit, 2 raised to 3 bit, R3 will be there, that will be R0 by 8. So in this way, the resistors of this resistor divider network are all having the different value. That is the one headache. So that is the one, what is the one headache one? Because these resistors, these dividers, resistor dividers are usually constructed by using precision resistors. So the added expense becomes more as the resistors used in the resistor divider network are of different value, and precision is another biggest problem. We will have to use the high precision resistors. So you will have to use the different kinds of precision resistors. So that increases the expenses of the circuit. And as we have to choose a different value of resistors, the precision also becomes the headache. So these are the drawbacks of resistive divider network, and these are the basics of a resistive divider network, simple circuit, and these drawbacks are removed in another type of network which converts a digital signal into an analog one, and that is called as the binary ladder network. So this is a very good, very famous network which is used to convert a digital signal into a binary signal called as the R to R binary ladder circuit. So in the next class, I am going to explain this R to R binary ladder network. Thanks for listening.